Okay, so here's our big problem. We're actually only going to work through parts A and B together here. I encourage you to try doing part C on your own. I've got the answers provided here for what you should get for all three parts. Now, hopefully part A is pretty straightforward. This is very similar to a kind of question that you'd see in chapter 18. Basically, if we were to have a salt solution, for example, we might have some weak acid. And again, here's a salt, which provides the conjugate base. So this is kind of like a problem we'd see in chapter 18. Then we're going to say what happens to that solution if we were to add 0.02 moles of sodium hydroxide. So this represents kind of a new calculation, new chemistry that we've seen. We're sort of thinking about adding this all at once, so there's no volume changes we need to think about. You've done stuff with titrations in lab, and we're going to get to titrations in our next lecture, but this one really is all about just adding this chemical to solution and not really thinking about it doing anything to change the volume. We're just going to be using 0.02 moles, in this case, of strong base in B or strong acid in C. So what we can see here is we have a starting pH of 4.74 with our buffer. If we add in some strong base, we see a slight increase. If we add in some strong acid, we see a decrease. So let's work through part A here. And again, if you want to take a stab at trying these on your own, go ahead and pause the video. If you want to kind of watch through the worked out solution, feel free to just let it play. Okay, so if we think about this first part, haven't done any chemistry, we just have a buffered solution. So thinking about writing the species, who's in solution? Well, we've got an acetic acid solution that they said is 0.5 molar, and we've got a sodium acetate solution that's 0.5 molar. So even though we've got sodium that's there at 0.5 molar, that's a spectator ion. Remember that from chapter 18? We don't see any acid-base or pH changing chemistry with sodium ions. So it's a spectator ion. So this is what we have in solution that's relevant to affecting the pH. Because we haven't added anything to our buffer, there's no chemistry that we have to think about. For the problems that we're going to work through in this section, there's no changes in volume because we're just, even in our next problem, when we add something, we're not changing the volume. So we're going to treat this problem just like we've treated all of our problems previously. Start with a balanced chemical equation. This is what we can have happen when we have these species in solution. We've got a weak acid that can dissociate into its conjugate base and H3O+. Because this is an acid equilibrium, we're going to want to be using a Ka value. Now let me highlight, you could have just as easily written this reaction in the opposite direction. That would have been totally fine, but you would then have to use a Kb value. Okay? Icf tables that contain molarities. Now this is the one piece that's different from what we did in chapter 18. In chapter 18, you might have only seen a problem that said, what's the pH of a 0.5 molar acetic acid solution? Or a 0.5 molar sodium acetate solution, not a solution that contained both of them. So this is a piece that's new, and don't get tripped up by this. Don't put a 0 in here because it's not 0. They tell us that we start by having that amount of both of these chemicals, 0.5 molar, weak acid, and conjugate base. Now again, this is where it might get a little bit confusing whether you put plus x's or minus x's, but as we're going to see on our next slide here, because we make an assumption that x is small and the x's are going to go away, it doesn't matter whether it's plus x or minus x here. So don't worry and stress about that, because for this ice table, it's not going to matter because we make an assumption that x is small. Propagate your values here in your ice table to get 0.5 minus x, 0.5 plus x, and x. So I'll give you a minute to kind of let this sink in and think now again about what this means. How would we solve this ice table to essentially get our X, because that's going to determine what H3O plus is. So moving on to solve for X, we're going to treat this like we did all of our other problems where we were solving for X. We're going to have an equilibrium expression. Because we wrote an acid equilibrium, we need to make sure we use a Ka value. We still want to make sure that we're thinking about the same principles that we talked about in chapter 18 when we think about doing an assumption. So you can either do a pre-check or a post-check to make sure that we're okay making our assumptions. But putting in those values that we have, we're going to have a 0.5 plus X on top and then a 0.5 minus X on the bottom. And again, seeing that we make this assumption here, it's not going to matter whether it was a plus or a minus X because we're assuming our X's are small and they go away here. So again, don't worry about that. But we're going to see that because these values are the same, they actually cancel. So our X in this case is going to be equal to the Ka value. Take the negative log of that X, right? And that's going to be equal to our pH. See if this makes sense. This is also our Ka value. So taking the negative log of it is our pKa value. So remember when we talked about the concentrations of weak acid and its conjugate base being equal? We said that pH would be equal to pKa. So we can see that play out here if we solve this with an ICE table. And I want to encourage you to still use ICE tables if that's what's most familiar to you. But I want to show you how simple this calculation can be. If we know we've got a buffer solution, we can use the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation will give us pH when we put in the pKa value, which again is just the negative log of Ka, plus the log of what our conjugate base concentration is, plus our weak acid concentration. Those were these values right here. Because these were equal, we're going to have the log of 1. The log of 1 is 0. So again, here we see that pH is equal to pKa. That's what we, in essence, got to the same answer going through an ICE table. So again, I wanted to show you that you can solve this problem using chemistry that you already know, which is an ICE table, and then solving for X. But importantly, you can very simply use a new equation anytime you know you have a buffer. And you have to have a buffer. You have to have a weak acid and its conjugate base. You can use the Henderson-Hasselbalch equation and just put those two values in, put the pKa value in, and solve for your unknown. Very simple to get pH when you know you have a buffer solution. Okay, moving on to the last little piece here. Let's imagine that we are going to add some base to this. Okay, so we're going to add 0.02 moles of sodium hydroxide to this. We're going to assume that there's no change in volume, so we're still going to have 1 liter of solution. This is something that's going to change. This is going to be an important player when we get to titrations in our next lecture. But if you want, take a stab at working through that problem. Again, highlighting, we know that the pH is going to increase a little bit. See if you can do the chemistry that gets you to 4.78. So start by writing who's there, identifying the chemistry that can happen, keeping track of it with an Icf table. We just said there's not going to be anything to consider with volume changes. But then once the chips have fallen, once the chemistry has happened, look at what you have left, and then you can either do an ICE table or again the Henderson-Hasselbalch equation to figure out pH. In my worked out solution, I'll actually show you both again. So pause the video here if you'd like to try this on your own, or let it play if you want to see the worked out solution. All right, so thinking about who's there. We still, again, have our weak acid and our conjugate base, remembering that that sodium is not going to have any impact here. It's a spectator ion. We've got 0.5 molar each we've got a liter of each. The new piece is that we've added 0.2 moles of sodium hydroxide. Again, sodium, from that sodium hydroxide being a spectator ion, the only player is that hydroxide that we've added. So we've added 0.2 moles of this. If we know how many moles of our weak acid that we have, we can tell how much of that soldier is going to be depleted, how much of that army is going to be depleted by the amount of hydroxide that we add. So we need to convert use the molarities in the volume here to figure out how many moles of acetic acid we have. This really represents the size of our army. We've got 0.5 moles of our weak acid army, and we're adding 0.02 moles of a strong base. So that's going to deplete this by a little bit. Not completely, but just a little bit. And we can use an Icf table to determine how much. So pause the video here if you want to try working through the Icf table on your own, or let it play if you want to see it worked out. So here's our Icf table. Just another little review here. When you have an Icf table is going to be used when you have chemistry that looks like this. One-way reactions, not equilibria. We need to have moles in our Icf table, not molarity. And we don't ever see variables in this part of our chemistry here. We're just using an Icf table as a way to keep track of everything that's going on. So we write the things the same way in that we start with a balanced chemical equation, but not for an equilibrium, for the chemistry that's going on. The chemistry that's going on is our weak acid army is going to sacrifice itself for the base that's added. We're going to generate some of our conjugate base army, neutralizing the hydroxide to generate water. Keeping in mind that there has to be moles that are in this table, we know that we've got 0.5 moles of our weak acid army, and we're adding 0.02 moles of our hydroxide army. This becomes our limiting reagent. We're going to use all of it up. So because we know the amount that gets used up here, that determines the amount that gets used up of our weak acid army. So we're left with 0.48 moles of our weak acid army. We've neutralized all of our hydroxide, and importantly, we've added 0.02 moles to our conjugate base army. Now, this chemistry became a little bit easier, or these calculations, I should say, became easier because we have 1 liter of solution. The number of moles that we have works out to be the molarity of that solution after all the chemistry has happened, after all the chips have fallen. This is what has happened. Our weak acid army's concentration has gone down, our conjugate base army has gone up, and we have neutralized that hydroxide invader. So now that we know the new concentrations of our species, pretend like this is a part A problem. Figure out what the pH of the solution is now that these are different from 0.5 and 0.5. So pause the video if you want to try that on your own, or let it play if you want to see the worked out solution. So again, we can treat this and solve this via an ICE table. So again, we've got our new concentrations of weak acid and conjugate base. So using the equilibrium that we'd think about that would exist between these, we can start by writing our balanced chemical equation there for our equilibrium reaction. Because we have an equilibrium that we have there, we're going to have an ICE table. So here's our ICE table. Again, our ICE table here is going to have these new values here. Not 0.5, but 0.48. Not 0.5, but 0.52. Treat this the same with our minus x's and our plus x's. And again, it really doesn't matter whether they're minus or pluses because we're going to do these assumptions that allow them to go away. But what I want to highlight is the only part that this becomes different from what we had in problem A is rather than these being 0.5 and 0.5, our weak base army is a little bit bigger. Our weak acid army is a little bit smaller. Calculations become exactly the same to go through and solve for X. X again gives us our H3O plus concentration. Negative log of that gives us pH, which is a little bit elevated because we added hydroxide to our solution. So again, you can solve this problem using an ice table, but you can also solve the problem, and I don't have it shown here, doing a Henderson-Hasselbalch equation. You could put in that the concentration of your conjugate base is 0.52, the concentration of your weak acid is 0.48, and you will still get the same answer of 4.78.